Hello and welcome to another Math for Honors lesson. I'm Kirk Weiler, and today we're going to be looking at more work with logarithms, while at the same time getting rid of this box. Alright, now remember the premise of all the work that we do in Math for Honors with logarithms is that you've actually had some exposure to them in previous years, especially in Algebra 2. I think that much of what we do today, though, could be helpful if you're in an Algebra 2 course, but remember, I'm going to assume that you have some basic familiarity with the log laws, which are then shown in that box. Keep in mind that all of these log laws, as we've discussed previously, are simply extension of exponent laws, right? This idea that the log gives you an exponent as an output. Therefore, if you multiply two quantities together, let me get my inking started. Man, I tell you. If I multiply two quantities together that have the same base, I end up adding their logarithms. If I divide two quantities with the same base, I subtract their logarithms. This one's a little bit tougher. This is that exponent law that says if you have something raised to an exponent raised to another exponent, you can then multiply the two exponents. But that's a little bit more of a stretch to see. Okay? So, let's take a look at how really familiar you are with these laws. They're very abstract, and a lot of people mess up their form very often. So if you ever find yourself messing up the form of a logarithm, you are not alone. They're very abstract. Let's take a look at exercise number 1. I like this exercise because it asks us to classify each of the following logarithmic statements or equations as true or false. And really, maybe the better way for me to say this is, which of the following are identities and which aren't, right? An identity is any equation that is true no matter what value of x and y you put in, as long as those values are within the domain of the function. So the question is, which of these are true statements and which are not true? Pause the video right now and take an attempt at this. This is a really good marker on whether or not you know your log laws. Okay, let's take a look. What I'm going to do is, at the beginning, I'm just going to write down what each one is, whether it's true or false, and then we'll especially talk about the false ones, but we'll also get into the true ones. So letter A is a false statement. Letter B is a true statement. Letter C is also a true statement. And letter D is a false statement. So we have two of each. So let's take a look at the false statements first, and really understand, if you will, the misconception that this statement is trying to pull you into, right? The log law with multiplication is very specific. It says that if we find the log, base anything, but of course here we have base 10, if we find the log of a product, that is always the equivalent of summing the individual logs. Even if the product involved more than two things, if it involved 3 or 4 things, we could sum all their logs. Here, this statement, that doesn't say the same thing. This says if I take the log of x and I multiply it by the log of y, I get the same thing as if I added the two logs together. No, that's just weird. I mean, it's really out and out weird, okay? The log of x is a number. It depends on x, but it's a number. The log of y is a number that depends on y. So that statement would be to say, if I take two random numbers and I multiply them together, I get the same thing as if I add the two numbers together. That doesn't make any sense. Let's take a look at letter D. Letter D is trying to get students to say, oh, I know that ln and e are inverses, so I can just cancel this and I'm left with 1/3. Now, that's not the way it works, right? The way it works is that the natural log is the same as the log base e. Yes? So I can think of it like this. But then that's asking, what do I have to raise e to get 1 over e cubed? The best way to really think about that, in my mind, is, well, write e to the 1 over e cubed as e to the -3. In this case, we now can cancel these, and we get the real output, which is -3. Alright, so that's why it's not true. -3 and 1/3 just aren't the same number. Now, letter B is definitely true. What's interesting about it is it's written in sort of the opposite order of how you typically think about logs, right? We typically think, oh, if I have ln of x cubed, I can bring the 3 out. But you also have permission to go the other way, right? So if I had 5 times the ln of x, I could bring that 5 in, and I'd have ln of x to the 5th. If I had something like 1/2 times the ln of y, I could bring that 1/2 in, and I could say that's ln of y to the 1/2, or ln of square root of y. if that was necessary. All right, letter C, this one's definitely true as well, although I think some people probably put false. Now keep in mind, this is just a direct application of the division law for logarithms, which says that if we have the log of a division, we can break that up by subtracting the log of the denominator from the log of the numerator. So I have log x minus log of 1,000. The 3 comes from the fact that the log base 10 of 1,000 is 3. Now some students say false because they look at this and they wrongly interpret the order of operations. Now if you think about order of operations, right, please excuse my dear Aunt Sally, parentheses, exponents, multiplication, division, addition, subtraction. There's nothing in there that mentions logs or trig functions or all sorts of other more complicated functions that you might come across. Generally speaking, addition and subtraction is always subordinate, meaning comes after, any higher level operation. All right? So log of x minus 3 is not the same as the log of quantity x minus 3. These are not equal. Let's go on to the next exercise. All right, this is kind of a classic and certainly one that you could have encountered before at the Algebra 2 level. Here we come up with some equivalency. We're told that x is equal to the log base 10 of m, and y is equal to the log base 10 of n. Now, keep in mind, folks, those equality symbols are really key. It means that anytime I see log m, I can put in an x. Anytime I see log n, I can put in a y. But then the problem challenges me to rewrite each of the following expressions in terms of x and y, meaning my final answer has to have x and or y in it, and I can't use any logarithms. Where's that other? Without the use of logarithms. Highlight that, right? No logarithms in my final answer. So what I'd like you to do is I'd like you to pause the video right now and see if you can manipulate each one of these quantities so that your final answer has either x or y or both in it and has no logarithm in it. All right, pause the video now. One of, I think, the greatest ironies of this problem is that perhaps the hardest one of all is letter A. Right? People look at this and they go, well, what am I supposed to do with this? Right? Well, think about it. X is equal to the log base 10 of m. We can actually rewrite the exponential equivalent expression or equation, right? So saying that x is equal to the log base 10 of m, which is this statement, is exactly the same as saying that m is equal to 10 to the x. And that fits the bill, right? We're now in terms of x, and there's no logarithms. All right, so let's take a look at the next problem. The log of the cubed root of m. I'm hoping you got 1/3 x here or x divided by 3, right? Because what I'd be looking at here is I'd be saying to myself, okay, I have the log of m to the 1/3. Right? My logarithm property tells me that that is exactly equivalent to 1/3 times the log of m. But this is when I have to realize what the fundamental property or the substitution property of the equality says, right? If two things are equal, I can always replace them with one another. So since log base 10 of m is just x, that's 1/3 x, or x divided by 3. Letter C. Many students will get letter C right, except for a little bit of a subtraction issue. But I like this one because it's a structural problem. Now, here's the thing, right? Every log law, every one of the log laws is involved in letter C. But what you have to think about is the bigger structure. The bigger structure, or the biggest structure of all, is that I'm doing the log of something divided by something, right? So my big log law that kicks in is the division law, right? This is going to be the log of m squared, and if parentheses are helpful for you, put them there, minus the log of 100n, right? The log of something divided by something is the log of that top minus the log of the bottom. Sorry for my poor terminology, especially if you're a math teacher watching this. Now, of course, this we can use the third log law on, and we can pull out that 2. We can say that's 2 times the log of m. Now this one, this is where students will make mistakes because they'll realize that they have to use that product, right? And this is going to be the log of 100 plus the log of n. And now I've made a little mistake. See if you understand what my mistake is. I'm going to pause the video for a second. I'm having a little bit of a problem with my pen slowing down. Not really sure why. Sometimes this clears it up. If I'll ever understand CPU usage on a computer, that'll be great. I'm going to eventually be moving these videos hopefully over to a Mac. That generally does a better job than a PC, but you know, Bill Gates, please don't come after me. Anyway, so did you figure out my mistake? My mistake is that I really need to subtract all of this, right? I can't just subtract some of it. Now, of course, log base 10 of m is x. We were told that. But now we have to subtract the log base 10 of 100. Well, that's 2. And then we have to subtract the log base 10 of n, and that's y. So this is a great way to leave your final answer. 2x minus 2 minus y. If you have 2x minus 2 plus y, that's because you didn't distribute that subtraction. Alright, let's take a look at exercise 3. Exercise 3 is a very, very easy problem. And I say that because you might do it very quickly and say to yourself, well, what was the point of that? Right? And the point of that is actually exercise number 4. So let's do exercise 3. In number 3, it asks us to find the values of k to 4 decimal place accuracy. And then it's very simple. E to the k equals 7 and e to the k equals 1/2. Alright? So this is pretty easy, right? We're just going to use that last logarithm property, or better yet, not even that. We're just going to use the inverse nature of logarithms.
Bob Siniscalchi, please come to the main office. Bob Siniscalchi to the main office, please.
Or as we like to call him at Arlington, AV Bob. Hi, Bob. Anyway, so if you take the natural log of both sides, the beautiful thing is the ln and the e would cancel, and that just leaves you with k. You could do it, you know, doing natural log or base 10 or other bases. But if your base is e, do the natural logarithm. So obviously, the exact value of k is the ln of 7. Keep that in mind. That is an exact value. But if I type that into my calculator, I would find a 4 decimal place accuracy 1.9459. If you haven't already done letter B, please do it very quickly. Alright, let's make sure you have it. Literally, I mean, I don't even have to think about it as the log of both sides. This is the equivalent logarithmic equation for this exponential equation. Now, in order to get the correct answer, I actually have to put it into my calculator. And it would be negative 0.6931. This is actually a very famous logarithm, believe it or not. Due to radioactive decay, the natural log of 1/2, being negative 0.6931, comes up a lot in chemistry and other areas of engineering and decay modeling. Alright, now we're going to loop back at this point, and we're going to talk about exponential modeling more from previous lessons, but now we have the logarithm, you know, sort of at our disposal. Now remember, when we modeled with exponential functions, we really had two primary forms we worked with. We had y equals a times b to the t. This was a situation where, you know, you knew sort of the percent that something was growing, the effective percent that it was growing at for a given time period, right? And that effective percent kind of got wrapped up in the value of b. A, of course, is just our initial value. And then we had this other way of modeling using e, right? And in this idea, right, in this problem, the idea is that k was what was called my continuous growth rate, right? And it was always a nominal rate, in name only. The b, that gives you the actual effective rate. So let's take a look at number 3. Okay. It says, consider a population that's growing according to this formula, 250 times 1.035 to the t, where t is measured in years. Alright, never trust the amount of space I give you to do a problem. Sometimes it's just the way the worksheet works out. Letter A says, determine the annual percentage growth rate. Now, based on the fact that they don't talk about nominal or effective, then they're talking about effective, okay? I mean, if we leave it out, if we leave nominal or effective out, we're talking effective. Now, if this seems very easy to you, it's because it is. Pause the video now, though, and think about it for a second if you don't know what the right answer is right off the top of your head. Alright, hopefully you do know what the answer is, right? To figure out effectively what we're getting, we just have to look at what we're multiplying by. Since we're multiplying over and over again by 1.035, what we can definitely say is that we have a 3.5% yearly rate. And that's an effective yearly rate. Now, letter B says convert the model into P equals AE to the KT. Write K to 4 decimal place accuracy. What is the continuous yearly growth rate? Now, by the way, a lot of times students wonder why. Why do we need the two forms? In calculus, it's going to be much, much better to be able to model exponentials with a base E rather than other bases. In fact, if you were working with some kind of commercial spreadsheet program like Excel, and you asked it to do an exponential fit on a set of data, right? Well, fit it with the best exponential. It will almost always give it to you in the form A times E to the KT, right? So it says convert it into that model. Now look, you got these two models, right? You got 250 times 1.035 raised to the t, and then you've got a e to the kt. Alright, one thing is very easy. It's a. A is 250. The key now is in realizing that the e to the k is equal to the 1.035, right? So, since that's the only thing, the only parameter that's missing in my problem, all I really have to do to get it into the form a times e to the kt is solve for k, right? And in fact, I can solve for k by taking the natural log of both sides. That's exactly why we did the last problem. To very quickly do this, it says write k to 4 decimal place accuracy. All right, we really want k to be quite accurate. Most of the time in a realistic setting, what we would probably do is just leave it as the natural logarithm of 1.035. But I actually like to write it out a little bit. It's 0.0344. So our model now would be P, again, sluggish CPU. No idea why. 250 to the 0.0344t. And then what we would say is we would say that its continuous growth rate is simply 3.44%. Now remember, that's nominal. Effectively what we're getting is we're getting 3.5% per year. But if I were to say to somebody, hey, what's my instantaneous or my continuous growth rate, I'd say 3.44%. All right, exercise number 4. A radioactive material loses 5.9% of its mass per hour. What is the mass's half-life? Round to the nearest tenth of an hour. All right, I want you to pause this video. I want to see if you can figure this out, right? So try to do it. Try to model the problem. Try to use logarithms to solve for the final answer. See where you can get. How long does it take for half of the material to remain radioactive? Pause the video now. All right. Hopefully you found out that the final answer was 11.4 hours. 11.4 hours. Now, one of the keys here, one of the many keys, is realizing that they don't say that it's a continuous loss, right? If so, we could go with our P times e to the RT, right? Or P times e to the KT, however you want it, right? So what we really want to do is we're gonna model it in this situation with our more standard model, a times b to the t. The question is, what's b? Now, what you really don't want to say is that b is 0.059. We are always modeling what remains, not modeling what we lost. So to really think about what remains, I have to think about what 100 minus 5.9% is. 100 minus 5.9% means that 94.1% remains after each hour. 94.1% remains of what we had previously. So we can model the amount that we have as some initial amount, which we don't know, times 0.941 raised to the t. Now, what I really want to know is what value of t will make this thing equal to 0.5 or 1/2, whatever you want to think of it as, right? The a is actually irrelevant. I want to know how long it takes for my multiplier to be 1/2. So I'm just solving that equation, right? I'm solving 0.941 to the t equals 0.5. Nothing to do with continuous growth rates. I can now do the log base anything I want of both sides. I'll typically take the natural log. If I did the natural log of both sides, I'm going to skip a step here because the video quality is not that great right now. The mouse is a little bit hard to control, but we'll get through it. Right? If I take the natural log of both sides, and then of course I can divide by the natural log of 0.941 on both sides to get my final answer. I'm just going to draw this line over here. And what we'll end up having is t equals 11.4. And watch your units. It would be so easy. I think I did this originally on my notes. It would be so easy to put in the units of years. But remember, we're decaying, and our unit of time is hour, or hours here. 11.4 hours. That's kind of a neat problem. I like it. Let's take a look at number 5. Number 5 says a population of a town doubles every 8 years. Interesting. Every 8 years we get to multiply by 2. What is the annual growth rate? What is its continuous yearly growth rate? Round both to the nearest 100%. This is a pretty long problem, actually, so what I want you to do is pause the video and really think about this. And if you were with me for our lesson on repeated percent growth, this may end up being very quick for you. Pause the video now. Alright, so first let's attack just the typical model. And what I mean by the typical model is that we're thinking about population being modeled like this. A times b to the t. And what we know, right, is that we know that when we raised that base, whatever it was, to the 8th, we doubled our result. So we could set it up more formally. We could say a times b to the 8th equals 2 times a. But again, it's all about this, right? What will it take to get that to be 2? Very, very simple, right? We're going to just raise both sides to the 1/8 power, right? This is what we were talking about a few lessons ago when we said, you know, if we know it's doubled in 8 years, we can figure out what happens every year by going backwards by using a root, right? Anyway, we'll put that into our calculator. We'll get 1.0905 ... right? We want to round this to the nearest 100%. That's going to be 9.05%. Now, that's really the effective growth rate. That's effective. In other words, every year, at the end of the year, if you wanted the new population, you would just multiply by 1.0905. But then it asks us for what our continuous yearly growth rate was. Now, with the continuous form, right, what we have is y equals a e to the kt. And remember, the way to look at this is that what we've really got is exactly the same model. It's just that b is equal to e to the k, where k is that continuous growth rate. So what I really have is that e to the k is that 1.0905. I think I'd want to be pretty accurate here. If I really needed to, I could just put in 2 to the 1/8 over here. But now, of course, we can find the value of k by taking the natural log of both sides, 1.0905. And this actually will be the rate. This gives me 0.08664, etc. So we have a nominal, in name only, we have a nominal rate of 8.66% continuously. Alright, let's do one final problem that's actually pretty easy. I just want to make sure you have a little bit of skill in this. Most of the time we translate from sort of the standard a times b to the t form into the less standard, although probably more commonly used in the real world, a times e to the kt. But sometimes we want to go the other direction, and it's actually really quite easy. In exercise 6 it says, given y equals 7 times e to the 0.135t, we want to write it in the more standard y equals a times b to the t form. But again, look at how kind of easy this is, if you will. right? If we kind of, if we stack, I don't know why I just wrote that completely wrong. Get rid of that. Should never use highlighters and erasers. Oh no, now I got sluggish growth. Anyway, if I write down my model, and then I write down the alternative form, remember we want the two models to be identical, or better yet, we want the models to give identical outputs for identical inputs. If we look at these two, it's very simple, right? Okay, A is going to be 7, so that's no problem. All we have to do is figure out what B is. But again, what B is simply this multiplier. So it's very, very simple. And that was the same relationship we saw in the last one. It's just that we were doing the harder thing, right? We were actually having to do some logarithms and things like that to figure out the value of K. Here we just need to figure out the value of B, so we end up doing e to the 0.135, again obviously on our calculator, and we have 1.144. Right? So our actual model in the more standard form would be 7 times 1.144 raised to the t. Oh my goodness, it's like the cursor is 2 seconds behind where my hand is. Very strange. Alright, well that's our lesson for today. Thank you again for joining me. I'm Kirk Weiler, and until next time, keep thinking and keep solving problems.